Good morning. This is Steve Hudson with Powermetrix. Welcome. Today we're going to talk about an introduction to harmonics. This is the latest in our COVID-19 quarantine webinar series. We've been doing this for almost 4 months now, and just want to give you the upcoming schedule. Today, of course, we're going to talk about harmonics. On Thursday, you'll be meeting with John Jones to talk about designing a meter installation. That'll be a lot of fun because basically John's going to go over all the key parts in a meter installation and tell you what important things that you need to pay attention to as you're designing new meter installations. Next Tuesday, I'll be back with you and we'll be talking about standards, traceability, and accuracy. Basically how important it is for your meter to be accurate and how do you verify that and how do you make sure that that's traceable to a national standard so that if there's ever a legal ramification that you know how to take care of that. Then finally, next Thursday, we'll be talking about billing versus metering accuracy. Basically, that's one of our key presentations that we give around the country, talking about if you test a meter, is that good enough? Or do you need to be looking at other things? If you test the meter, does that guarantee that the customer gets an accurate bill? And the simple answer to that is no. But tune in next Thursday and you'll learn more about that. All right, so we're going to go ahead and get started with our harmonic presentation. The focus of the presentation today, first of all, what's the definition of harmonics and what's some basic theory behind those? What are harmonics as they relate to electric power? Harmonics are present in many different things, not just electric power, but we're going to stay focused on that since, of course, that's what we care about. What are some common sources of harmonics in electronics? There's a few things out there that may surprise you. And then finally, how do these harmonics affect metering and other equipment in power distribution and measurement? Basically, we talk a lot about harmonics, but the bottom line is how does that affect the metering and how does that affect our job? So we'll talk about that. So let's go ahead and jump into the big question. Question number one is harmonics, what are they? Well, if I look in the dictionary, the mathematical definition of a harmonic is a component frequency of the signal that is an integer multiple of the fundamental frequency. Now, if I go and turn that into more normal English, basically what I'm saying there is that a harmonic is a part of the waveform. When I'm talking about a waveform in electric power, we're talking about a voltage or current that is an integer multiple of the fundamental frequency. Now, in the United States of America, our operating frequency, our fundamental frequency is 60 hertz. And so if I start talking about harmonics of that, it's an integer multiple. So that's going to be like 2 times, 3 times, 4 times. So for example, a second harmonic would be 2 times 60 is 120. Third harmonic would be 3 times 6 would be 180, and so on and so forth. Harmonics describe a disturbance which repeat every cycle. Now that's very important. That's important. The key word there is repeat, meaning that the harmonic occurs basically as long as you have power applied to a system. It can be differentiated from other sorts of power quality issues. A lot of times harmonics are, of course, bound up in the overall arching theme of power quality. But we're going to talk about the differences here in just a second. Just to give you a little history on harmonics, engineers and mathematicians basically analyze harmonics using something called Fourier analysis. Fourier was a French mathematician that lived back, I believe, in the 1800s. That figured out a really cool thing about periodic waveforms, which is that you can take any periodic waveform and you can apply a Fourier series basically to figure out the constituent parts of that. You can break it down into sine waves and cosine waves. And below here you see the base formula for that. If we use a graphical example to make this a little more clear, this day we start out with a 60 hertz fundamental. That's the dark blue waveform that you see on your screen. That's ideally what you have coming out of the generator when you're generating voltage. If we go and we apply a fifth harmonic, that'd be 300 hertz. That's the sort of the hot pink waveform there in the middle of the screen. And we sum those two waveforms together using Fourier analysis. What you end up with is the light blue signal, which you see it still looks very similar, sort of follows along the 60 hertz, but it's got a lot of waves on top of it. And so in the modern world today, a lot of the times the waveforms that you see are going to be much closer to that blue wave, the light blue waveform than the dark blue waveform. Very rarely do we have really a pure sine wave anymore, certainly in the current side. Voltage is still pretty clean, but current can be really, really bad. And we're going to see some examples here of that in just a minute. Here's another good example. Basically what we did was we started out with a 60 hertz sine wave, once again the dark blue waveform, and we added more and more harmonics to turn that into a square wave. A square wave, a perfect square wave, is made up of an infinite number of odd harmonics, so odd being 1, 3, 5, 7, 9, 11, et cetera, et cetera. And so what we did there was we took the third, the fifth, the seventh, the ninth harmonic, and we added those all together, and at some point, basically, that ends up giving you this square-looking waveform. And believe it or not, of course, there are some power systems out there nowadays that do actually have a very squarish-looking waveform. And you'll see later in our presentation one of the applications of that and how does that affect the meter. All right, so in more detail, how does harmonics apply to power? Well, I said earlier that this is a repetitive contamination of a voltage or a current. Repetitive, once again, meaning that it happens every cycle. The harmonics are a function of the load, meaning that if I have a load, which is called a nonlinear load, basically what will happen is that that'll end up generating harmonics in my system. One of the most typical nonlinear loads that we run into nowadays are switching power supplies, and we'll see a couple examples of that here in just a minute. The problem with harmonics with power systems is that it produces a variety of infrastructural problems. In particular, harmonics likes to be burned up as heat. Harmonics is not useful power, first of all. It's not really doing the important work that we want to do. For example, lighting a light bulb, turning a motor. Most of the time harmonics end up going up in heat, and most of you all that have worked in the electronics industry for many years know that heat is not the friend of electronic equipment. Transformers in particular are really bad about the harmonics getting into the windings, heating up that transformer, and causing your equipment to fail or have to at least be serviced more often than not. And so as such, we try to minimize the amount of harmonics in our system simply by the fact that it causes a lot of problems. What we'll also see is that harmonics can generate system losses, both the heat losses, but also sometimes it can result in reduced metering, meaning that we're losing money because of that. We'll take a moment and stop and say, harmonics, what aren't they? We mentioned earlier that harmonics fall under the umbrella of power quality. Power quality can also include other things like sags, dips, and swells. Sags, dips, and swells is simply when we have a voltage system that's going out of regulation for a short period of time. It either dips down, sags, or it swells, meaning it goes up too high. A harmonic is not a sag or a swell simply by the fact that it doesn't occur really as over that period of time. What you'll see with a harmonic is it basically occurs each and every cycle. A sag, dip, and swell usually is averaged out over a longer period of time than that. A transient voltage, normally most folks think about transients, they think about lightning event. So that's a very intermittent event, may occur very rarely. Once again, it's usually a one-time only kind of event for any given period of time. Transients occur just once. Harmonics, once again, occur over and over again. The harmonic will continue to exist as long as you have the particular load that's being applied to that system. Then finally, frequency variations. Frequency variations basically mean, are we getting off of our ideal 60 hertz? And of course, our 60 hertz is pretty well regulated over the long haul. You will see minute changes in that, maybe to the order of 1/10 of a hertz over short periods of time. But a harmonic is not a frequency variation. Harmonics, of course, have a frequency component, given that it's a multiple of the frequency, but it is different than a frequency variation, because when we say frequency variation, we're really fixated still on the fundamental frequency and how that's changing. Harmonics, once again, you're talking about multiples of that base frequency, 60 hertz, 120 hertz, 180 hertz, so on and so forth. All right, these are all non-periodic kinds of power quality issues. Harmonics must be periodic, meaning they must occur at a given interval. Once again, the harmonic basically occurs each and every cycle of the sine wave, and as such, it will continue to exist until it's dealt with. And so that leads into the next question: where do harmonics come from? Well, once again, nonlinear loads at the customer's site. The best way that I define a linear versus a nonlinear system is that if you think about it in terms of a sine wave input or a sine wave output, Here, we'll use a graphical example. Let's say that we have just a simple resistive load. That's the most typical load we had, say, back 100 years ago. Light bulbs, stove eyes, heaters, things of that sort. When I say that's a linear load, what I mean is if I apply a sinusoidal voltage to a resistive load and I look at the current coming out, it's also sinusoidal. It's in phase, given that's a resistive load. Now, if I switch over to an inductive load is different than a resistive load in that it causes a phase shift. A phase shift, of course, is a time difference between the voltage and the current waveform. But guess what? That's still a linear load simply by the fact that my current coming out still is sinusoidal. I apply a sinusoidal voltage to an inductive load, I get a sinusoidal current out. And so inductive loads, while they do add lag to the phase, it is still considered to be a linear load. Let's go the other direction. Let's talk about capacitive load. Capacitive load, basically what happens there is the current starts leading the voltage. So once again, there's a phase differential, phase shift between the voltage and current, but you'll notice still that the current is still sinusoidal. You still get a linear response out of a purely capacitive system, simply by the fact that, I stick a sine wave in, I get a sine wave out. All right, so what's a nonlinear load? A nonlinear load, I mentioned earlier, the most classic example of that in modern society is a switching power supply. Switching power supply can be used for a variety of functions. Most of the time, what we use those for is doing an AC to DC conversion. Most all end products, a cell phone, a computer monitor, a TV set, even a refrigerator, believe it or not, most of the time nowadays run off DC power. And so in AC systems, basically, we use 120 volts, say in a residential. What we have to do is we have to basically put that through an AC to DC converter. I've got a little block diagram here that basically illustrates some of the functions of that. And so the first step is, of course, we take the 120 volts, we put through a transformer to step it down. We then put through the rectifier. The rectifier is the key. That's the nonlinear load. Those little diodes in the rectifier basically take that nice lumpy sine wave and start to flatten it out so it becomes DC. DC, you look at an AC waveform on an oscilloscope, it's nice sinusoidal. If you look at a DC level, it's very boring. It's just a straight line, basically. But really the rectifier is what's doing the job of turning that from an AC into a DC signal. We then put that through a regulator circuit, which flattens it out even more. But it's really that process of running it through the rectifier that causes that to become different. And so if you look at our waveform displayed there on the screen, if you look at the blue waveform in particular, you see the skinny blue waveform is the voltage, which still looks very sinusoidal. But now the darker blue, more solid waveform is the current waveform going through that switching power supply. And what you see is that you get a little pulse of current, basically, every time you hit the top and the bottom of that sine wave. And once again, that's that rectifier circuit working basically to draw a little slug of current every time we peak or trough in our voltage. It takes a little sip of that current and basically turns that into DC to use, once again, for all the different consumer electronics that we have out there. I mentioned earlier the refrigerator. That actually sort of shocked me. Last time I had to go out and buy a refrigerator, I was out at the appliance store, and in big letters they had a sign on the refrigerator that said, Energy Star compliant, direct drive motor. Well, once again, that direct drive motor is a DC stepper motor, meaning that not only do they take DC, but they basically switch it on and off and on and off and on and off. And both by converting it into DC and also switching it using that stepper motor, we add that much more harmonic energy to that. The good news is, that refrigerator is more efficient than an old refrigerator, say, with an AC motor in it, AC compressor, but there is a price to be paid. We'll see the details of that in here in just a second. Before we get more into the details of harmonics, how it's affecting our power, let's talk about how are harmonics measured. The measurement unit for harmonics is THD, which stands for total harmonic distortion. THD is the measure of the ratio of the sum of the harmonic power to the power of the fundamental frequency. So basically you can think of that as a fraction where on top I've got the harmonic content, the harmonic portion of the voltage or current, and then the bottom is the fundamental, the 60 hertz component. And so what we're going to see there is that the bigger the percentage of THD, the more harmonic content, either in the voltage or the current signal. And the bigger the number, really, the worse things get. We really want to try and keep that number as low as possible. But let me give you an example of that, just in terms of how things are summed together. So if I take a voltage, or a current, I guess in this case, and I basically say, okay, I've got a fundamental signal of 60 hertz that's 10 amps, and then I want to add a second, a third, and a fourth harmonic, and I'm going to add just a little bit. I'm going to add 3/10 of an amp on the second, 2/10 of an amp on the third, and 1/10 of an amp on the fourth. And I run it through that formula that I gave you before. I'm going to end up with a THD of 3.7%. Now I'm going to tell you right now, 3.7% actually is a pretty good number. You know, if you can get a current THD number less than 20%, that's actually really good by today's standards. In the second example, what you see I'm doing is I'll take 12 amps of fundamental current, and then I'll add 10 amps of second, 3 amps of third, and 1.5 amps of fourth. Of course, those numbers are a lot bigger than the numbers in the first example, and so as such, the THD number jumps way up, almost to 90%. Once again, that's not uncommon nowadays. We'll see a few examples here in a minute just to show you what I mean by that. The one thing I will note about THD is the THD can be greater than 100%. What that means is that your signal, your voltage or current, has more harmonic energy than fundamental energy. Keep in mind, harmonic energy is not your friend in a power system, because most of the time that's being burned up as heat. It's not doing useful work. It's making your equipment hotter, and so as such, it's wearing it out that much sooner. And so once again, you really want to try and keep that THD number down as low as you can, just to try and keep your equipment happy. If we take a moment and we talk about in the past, let's say over the past 50 years or even 100 years, what were some sources of harmonics? Well, believe it or not, one of the most common sources was a transformer. Transformer, it could be a distribution transformer, it could be even an instrumentation transformer. The problem is simply that if I try to get more energy out of my transformer than it's rated for, what I'm going to do is I'm going to end up putting that transformer in saturation. If we take the example of a PT, potential transformer, instrumentation transformer, and of course a PT, when you buy a PT, it's got a VA rating, that's its power rating. Basically that PT has to power everything on the secondary side of that, which most of the time is just the meter, but of course if you have other equipment on the system, it has to power that as well. I have a real good story that once upon a time I had a customer call me up, had a Powermaster system, I was testing out in the field and was having a problem. He called me up and said, "Hey Steve, I've got a Powermaster 7 series. I've been trying to run some tests on this thing, but this thing just won't power on." I said, "Well, Mr. Customer, tell me something about your site." He's like, "Well, I'm out at this site, it's a 9S site." I said, "Okay, 9S, transformer rated. Tell me, first of all, do you have PTs on the site?" He's like, "Well, yeah, I do." I said, "Well, where are you hooking up the auxiliary power on your Powermaster?" "Well, I'm hooking up right at the meter." I'm like, "Now wait a minute, let's stop. That's on the secondary side of those PTs. What are those PTs rated for?" "Well, they're 100 VA PTs." "Well, no, sorry, Mr. Customer, that Powermaster will probably draw upwards of about 1,000 VA. And so as such, you just put your PTs into saturation when you did that. And so if you'd gone and looked at the waveform coming out of the secondary side of that PT, what you would have seen is really more of a square wave than a sine wave, because it just couldn't keep up with that. And so as such, you might have had 20–30% THD on that system. So anyway, moral of the story is, if you got a transformer, pay very close attention that it's not being overburdened, because if you do, it will cause harmonics, it will cause things to heat up, it'll cause all sorts of good problems. Some other harmonic sources in the past, arc welders. Arc welder, of course, takes a really big slug of current at one time. It's sort of like that switching power supply. And so what you end up getting there is some odd harmonics, typically the 5th and 7th harmonics. Back in the olden days, you might get anywhere from 3 to 8%. Once again, that's still not too bad. A couple other examples, line community converters, static VAR compensators, saturable reactors. Once again, those are things that are drawing slugs of current, but once again, not generating really too much. You might get upwards of 30%, but in today's world, that's really not that bad. If we talk about new harmonic sources, one of the worst sources of THD nowadays is modern lighting. When I say modern lighting, I'm talking about green lighting, in particular fluorescent lighting, including compact fluorescence, or LED lighting. What we see there is that we get several harmonics on the order of sometimes way above 100%. The other thing, of course, as I mentioned earlier, was a switching power supply. Computers in particular use switching power supplies. Your laptop, your monitor, television sets nowadays, all those run off of DC power, and so as such, they've got those AC to DC switching power supplies. What we'll see there is, once again, a lot of odd harmonics, sometimes in excess of 100% THD. So once again, we said light bulbs. This is sort of my soapbox. Our newer light bulbs green. Big push nowadays, of course, to get everybody on board with green light bulbs, such as CCFL and LEDs. A lot of utilities over the last few years, of course, have been handing those out to customers, just trying to get them going. There for a while, the government actually talked about getting rid of incandescent bulbs. You couldn't buy them anymore. Fortunately, we still can. But they basically said, these things are great, they're awesome, there's nothing but advantages, so why would anyone ever want to use something other than that? Well, that's all true from a consumer point of view, except the dirty little secret about CCFLs and LEDs is that they generate VARs, and they generate a very high level of harmonics. So with that being said, let's look at a study I did a few years ago, which was a comparative study between 3 light bulbs. These were all light bulbs that were rated for 60 watt output. Of course, most consumers, when they think about light bulbs, they think about watts, 60 watt bulb, 100 watt bulb. They equate light output on wattage, which isn't, really the proper unit of measurement. A lumen is the proper unit of measurement. But anyway, for the sake of this presentation, the sake of this study, what I did was I took 3 bulbs, an incandescent, a compact fluorescent, and an LED bulb, and I got 3 bulbs that were all 60 watt equivalent output, which was probably about, 800-900 lumens. And what I wanted to see was, how did each of those bulbs fare in terms of the amount of harmonics being generated by that? And so we started out with our 60 watt incandescent bulb. Once again, an incandescent bulb is very simple. It's a resistive element, meaning that your current waveform is going to be in phase with your voltage waveform, have a power factor very close to unity. And so if I look at my watts, my VA, and my VAR, interestingly enough, this was called a green 60 watt bulb. And so even though it output the equivalent of 60 watts of light, it only consumed about 40 watts of active power, 41 watts. So that's pretty good. The reactive power was very low, less than 1 VAR. And so basically no phase shift, no VARs, very clean. And so the apparent power, once again, matched up pretty much to the active power. Oh, okay, hold on a second. We got a question from Rob L. Are there any strategies to devices to combat THD? Actually, yeah, we're going to talk about that at the end. Rob, thank you for the question. But we will at the end talk about some of the strategies in terms of how to get rid of that. So thank you for that. Keep the questions coming. Jared's going to keep monitoring that and let us know if there's other questions we want to talk about. But anyway, back to the incandescent bulb. With the incandescent bulb, once again, it's a resistive load. Our apparent power basically equals our active power, and then we get to the bottom, what we see is our current THD is 1.5%. We talked about linear versus nonlinear. If we look at our waveform, we look at our voltage, we look at our current, we've got a sine wave voltage going in, we got a sine wave current coming out, and so that's a very linear load. If we go and we switch over then to the 60 watt equivalent CCFL bulb, once again, that's compact fluorescent. First thing we're going to notice if we look at our watts is that, hey, that came way down. We went from 40 watts down to 14 watts. So basically that's a third, almost a third of the power. So once again, from a consumer's point of view, that's a really good deal because I'm getting the same amount of light. It's a light bulb. That's what I care about. I care about light output. I'm getting basically the equivalent amount of light for about 1/3 the wattage that I have to be putting into that. So the customer's looking at it, hey, that's a good deal. However, if I'm the utility company and I look at that, I'm like, well, okay, yeah, that's good. It reduced my watt burden. But if I now look and see at my reactive power, that compact fluorescent bulb is generating 6 VARs for 1 bulb. And so what that means is that those VARs are real energy. VARs are sort of misunderstood. If you all were with us a couple episodes back, you saw we had a funny example of the root beer, where the liquid in the root beer is the watts, the useful part. The foam on the root beer is the VARs. The reality of that is that it's still real energy. It still has to be generated, it still has to be transmitted, it still has to be paid for. The utility company pays for VA. It doesn't pay for watts. The customer, however, residential customers in particular, are being metered on watt hours. And so what that means is that those 6 VARs that are being produced by that compact fluorescent bulb are not being paid for by the customer, by the residential customer. They're being paid for by the utility. Most of the time, of course, that's just going to be lumped into what you consider to be line loss, which it's not really a line loss. But that's something that utilities need to be paying attention to, because that's just one light bulb. Think about the number of compact fluorescent light bulbs you've got out on your network, on your system right now, and just start to add that up. The other thing that I want to point out is the THD, 88%. You know, the incandescent bulb was only a couple of percent, but now we've jumped up to almost 88%. The reason for that being is that a compact fluorescent bulb basically does a frequency conversion. It takes 120 volts at 60 hertz and it steps it up to a much higher voltage, sometimes at a higher frequency. And so as such, it's considered to be a very nonlinear load. And if you look at the waveform on the left there, you see a sinusoidal, more or less sinusoidal voltage going in. There's a little bit of distortion. But you see a very ugly current. We've now gone from a sinusoidal looking current to something that looks more like a mountain peak. And once again, you see that happens each and every cycle, every half cycle actually. And so that contributes. Okay, we've got another question. Ricky asked the question, is it possible to have VARs without harmonics? Yes, Ricky, I think you can. The funny thing about harmonics is that it actually is made up of both watts, VA, and VAR. If you go and do the mathematics, you'll see that it can be broken down into that. I think to answer your question, it is possible, but you know, I'd be curious to try and find a system whereby we would do that. Tell you what, let me look into that and I'll get back to you. If you could, send your email to Jarrett and I'll be glad to respond to that. Maybe we'll bring that up in a later session. But really good question. Really good question. All right, so that's the compact fluorescent bulb. Let's go on to the LED bulb. LED bulb, once again, the 60 watt equivalent. Our active power is now down to 11 watts. Remember, we started out with 40 watts with our original incandescent bulb. So we're now down to, you know, basically 1/4 of the wattage being consumed by this. So once again, the consumer's going, hey, this is great, this is awesome. I'm saving all sorts of money on my electric bill, still able to light my house just as much as I want to. Utility comes back and looks at it, they're like, oh, hey, that's a problem in that, hey, we're still generating VARs. We got 4 VARs, 12 VA, but the real kicker on the LED bulb is the THD. We see now that the current THD has jumped up above 100%, 111%. What that means is that I've got more harmonic energy on the current on this bulb than I do fundamental energy. Once again, that THD, that harmonic energy is being dissipated as heat. If any of you all have ever changed an LED bulb, you know, after a couple of years you take the thing out, a lot of times the base is going to be yellow. The bulb itself runs really, really cool, but the base runs really hot. And the reason why is inside of that base, an LED is a DC bulb. I mean, that little base has an AC to DC switching power supply inside of it. And so that switching power supply is what's generating all those harmonics. And as such, the base of an LED bulb will get really, really hot. And so a lot of times it'll change colors to yellow, if any of y'all ever noticed that. And so the final example I want to give you is a laptop computer power supply. It's actually my laptop sitting over here in the corner. Consumes 35 watts of power. That's not horrible. But once again, 6 VARs of reactive power. And so our total VA is 37. But once again, if you look at the current THD, 144%. So almost 150% of the energy in this system is harmonic energy. Once again, if we go and look at the waveform, what you see there is I have a really sharp peak, sinusoidal voltage, but a really sharp peak on the peak and the trough of each and every sine wave, cycle of the sine wave. I will say this, the sharper the peak, the more harmonics are going to be generated. And some of these switching power supplies out there are just not clean at all. They're just really, really bad in terms of making a really sharp peak, really high amount of harmonics, and so as such that can really cause some problems for the grid. I'm going to take a side note here for a second and talk about a different way of looking at harmonics, an alternate approach. Another way we can look at harmonics is that they can be grouped into sequences. Sequences meaning plus, minus, or zero, positive, negative, and zeroth harmonics. If we look at the way that these are spaced out, we've got our fundamental, second, third, fourth, fifth, sixth. Basically, you start to see a pattern there. For the positive sequence, we have the fundamental, the fourth, the seventh, so on and so forth. For the negative, we have the second, the fifth, the eighth, and then for the zeroth, we have our thirds, our third, our fifth, our third, our sixth, our ninth, and so on and so forth. You're like, okay, Steve, that's very interesting. What does that mean in reality? What it means from a more practical point of view is that it's look at how those different harmonics affect a motor, for example. A positive harmonic, which once again would be our fundamental, our fourth or seventh. If we think about an AC motor that's turning in a certain direction, and we start to have a load that's generating those positive harmonics, what that's going to do is that's actually going to try and make that motor run faster. It's trying to push the magnetic envelope of that so that it's actually going a bit faster, which of course isn't really good for the motor. You know, if you're trying to keep it roll regulated, that's a problem. If we talk about our negative sequence harmonics, what that's doing is that's having the opposite effect. It's actually trying to slow that motor down, trying to pull it back. So once again, think of that generating friction, generating heat, and so that's a problem. Those are both bad, but really the real culprit are the zero sequence harmonics. Those are also known as thirds or triplets. The problem with that is that when you have a zeroth harmonic, is that what's happening is that all of the voltages and currents are summing together. Basically, they're all in phase. You know, an ideal power system, three-phase power system, you've got 120 degrees phase separation between that. And so if we have a system that has these zero sequence harmonics, what's happening is everything's summing together. Now the problem with that is, in the real world, is that on, say, a 4-wire Y, we have a voltage and we have a neutral. Ideally, the return current is supposed to go back through the neutral. Now on these currents, these zeros currents, basically, that's going to start going back through your ground conductor. And so a lot of times, the ground conductor in a system is not sized appropriately in terms of wire size. And so if you get too much current flowing through that can cause a lot of heat. In worst case, it can cause a fire. We actually had a story from a customer several years back out west that was a country club. Country club, of course, had a golf course, and they had just switched over their golf carts from gasoline golf carts to electric golf carts. And what happened was these golf carts, of course, are battery operated, meaning that they have to charge via DC. And so they had a big AC to DC converter to charge the batteries on these golf carts. And that AC to DC converter had really bad zero sequence harmonics. And so as such, it ended up dumping a lot of current into that ground conductor, so much that it caught the clubhouse on fire and burned it down. So once again, moral of the story is pay close attention, you know, when you specify one of these switching systems, because it can cause problems for your customer and for the utility. All right, so getting toward the ends now, let's talk about really what matters to us. How do harmonics affect metering? Well, back in the olden days of electromechanical meters, they didn't meter harmonics well at all. Electromechanical meter was really designed to measure the fundamental frequency of 60 hertz. And so what we saw was that by the time you got up to probably the fifth or seventh harmonic, you were losing 80% of that energy. It was still measuring the fundamental energy, but the energy content of the higher harmonics was being lost. And so what that means is that if I was just trying to measure the fifth or the seventh harmonic, I was basically losing about 80% of that. And so once again, if you had a system that had really high harmonic content, those electromechanical meters would not do a very good job of metering. And so that would be a loss to the utility. That's the bad news. Now the good news is we don't really live in the world of electromechanical meters anymore. We live in the world of solid state meters. Solid state meter, of course, is a digital device. It takes that voltage, it takes the current, it digitizes it, puts it into a little computer and does the math. The good news is solid state meters do a really good job measuring harmonics based on what's the sampling rate of the meters. Sampling rate basically goes back to the higher my sampling rate. If you think about a sinusoidal waveform, you think about little dots along that where I'm sampling it, say 10 times a cycle, 50 times a cycle, 100 times a cycle. The higher the sampling rate, the higher the level of harmonics I'll be able to capture that. And so, you know, most modern meters run at a high enough sampling rate that they're going to capture at least the lower level harmonics, probably at least up to the 20th order harmonic. Another problem we have with metering on transformer rated side is that CTs and PTs, of course, stand between the customer and the meter. And so once again, CTs and PTs were ideally designed to measure the fundamental frequency of 60 hertz. And so as such, there will be some attenuation of higher frequency harmonics on those CTs and PTs. I've spoken to a couple of IT manufacturers and found out, most CTs and PTs still will pass most of the lower level harmonics pretty well. Once you get up to higher orders, it will start to attenuate those. So once again, you could have some loss because of your CTs and PTs, just in the fact that it filters out the harmonics and the meter doesn't see it. The meter doesn't see it, the meter doesn't measure it, the meter doesn't charge for it. So just keep that in mind. Another important thing to talk about for those of you doing VA and VAR metering is that right now there is no standard definition for the mathematical formula for VA and VAR hours under harmonic conditions. That was a problem back in the day in that you could take a couple of different solid state meters, basically apply the same harmonic load to it, put it in a VA calculation mode, and you might get different answers. You might take 3 meters and get 3 different answers, as much as 50% different. And so as such, the ANSI committee, ANSI C12, which is our standards committee that basically defines what is a meter, how should metering be done, has been taking on the challenge of trying to figure out what is the standard formula for VA and VAR for a meter. And the good news is we're getting very close to making that. I actually sit on the ANSI committee that works on that. And so they've been working on it for several years, but they are getting very close, I think, to a definition for VA. VAR is a little more complicated. They may take that one on later, but hopefully we think within the next couple of years we should have a standard definition for VA. What that really means to the utility is once that's written into the standard, that means that all meter manufacturers will have to test against that formula, meaning that you will have consistent results when you're doing VA hour metering, independent of the meter that you buy. And so that's good news for the utilities. One important thing that the ANSI committee did do recently is that they made an update to C12.20, which is a standard that covers solid state meters. They added 6 sets of harmonic waveforms. These harmonic waveforms were taken from the real world. These are harmonic waveforms that did cause problems for metering in the past. And so now that it's been written as a standard, once again, that's part of the type test. That's part of anytime a new meter is designed, the meter manufacturers have to go and test against those harmonic waveforms to make sure that they get consistent answers in terms of the metering. And so we're going to go through each of these waveforms. The first one is waveform number 1, is called the 90-degree phase-fired waveform. We jokingly refer to it here in Powermetrix as the shark fin waveform, just because obviously it looks like a shark fin. What this is in real life is this is a dimmer switch, just like the one you have in your dining room. You push the button, you turn the knob, you can turn the lights down. Back in the olden days, basically, that used a little solid-state circuit, basically, to cut your sine wave in half. Half a sine wave means you're going to get half the power. Half the power means you're going to get half the light out. And so that was good for a romantic dinner with your wife, but the problem for the meter was that, basically, meters weren't good at measuring half a sine wave, simply by the fact that you had that really sharp edge, the sharp edge on the shark fin, that generated a ton of harmonics. And so as such, old meters had a really hard time trying to meter that properly. And so as such, the ANSI committee went and said, okay, we're going to add this waveform. This particular waveform, basically, they define it up to the 20th harmonic. Once again, most solid state meters will do fine up to 20th harmonic. Given that it's a sharp rise like that, you could actually go much higher. You could go up to, say, the 100th harmonic if you wanted to, but most of the energy is probably still going to be on most of the lower frequency harmonics. Second waveform is called the quadriform waveform, which is a switched load device. Basically, if we break that out into voltage and current, if we look at the voltage still looks pretty sinusoidal. We'll start to see a little bit of distortion there. But the current is very squarish, very square wave. And so once again, this is a switched device, maybe something switching on and off and on and off, on and off, a relay, piece of industrial equipment, something like that. If you remember early on in our presentation, we said a square wave is made up of basically, an ideal square wave is made up of an infinite number of odd harmonics. And so as such, this thing has a ton of harmonic energy in the current. And so once again, the meter once again, if it's an older meter, it might have a hard time measuring that. And so as such, that would result in a loss in metering. Once again, good news is most modern meters do a pretty good job with that. And now it's written in the ANSI standard, we have to test against that. Third waveform is a peaked waveform from a switching power supply. Once again, that's one of the most common harmonic loads that you see nowadays because those switching power supplies are everywhere. Once again, your cell phone charger, your computer power supply, your TV, even your refrigerator, washer and dryer, pretty much anything that's going to run off DC power is going to require that. And so you see the voltage, once again, is mostly sinusoidal. You'll see a little bit of an inflection in the peak and the trough, which if you overlaid those two waveforms would correspond to that big current peak that you see there. Basically, it tries to draw a big slug of current. The transformer responds in a little dip on the voltage, and so once again, you've got harmonics being produced on both sides. Waveform number 4 is the pulse waveform. This is also another form of switching power supply. So once again, you have a little bit more sharp peak on the current, a little bit more inflection on the voltage. Once again, much higher current harmonic waveform in this particular waveform set. Okay, waveform number 5 is a little bit different. This one's called the multiple zero crossing current waveform. If you ever looked at a sine wave and noticed, a sine wave ideally has one crossing. If we start out at 0, go through 180 degrees, that's our zero crossing, then back up to 360. Back in the olden days, a lot of meters were dependent upon that one single crossing point through 0 to be able to come up with a time base that ran on those meters. Once we started adding loads that generated these multiple zero crossings, you see the current waveform, it's all over the place. It crosses 0 1, 2, 3, 4, 5, 6 different times. That's a problem because that would really confuse the clock inside of those meters. It's not 60 hertz anymore. It's going to be a much higher harmonic than that. And so as such, the meter would just sort of go nuts and give really bad registration. So once again, that was a very important waveform that needed to be rectified. And so once again, the ANSI committee went and added that to the standard so that could be tested for. Waveform number 6, of course, is sort of the opposite of that. You've got a zero crossing voltage waveform. And so now I've got a square wave, basically on my voltage, and a sine wave on my current. Now, I'll be honest with you, I don't know that you'd ever have a real system that would have a square wave voltage with a perfectly pristine current waveform. I think the current's still going to look a little odd. But anyway, the point being that the reality of this waveform, this was based on a cheap AC inverter. If you go down to the hardware store, buy an AC converter that you can plug into your cigarette lighter adapter, if you looked at that voltage output with an oscilloscope, that's what you're going to see. You're going to see a square wave. Once again, a lot of harmonic content, given that's a square wave. Really bad for your equipment. I will say personally, I've gone through about maybe 2 or 3 different computer laptop power supplies, trying to use those cheap inverters. If you want to invest, get you a pure sine wave inverter, basically meaning that it filters out all the harmonics for you if you care about your equipment, because once again, that square wave, it's not going to do your equipment any favors. All right, so now finally we get to the question that was posed a little bit earlier. We've got all these harmonic problems. What do we do about it? How do we fix it? Well, the problem with harmonics is that harmonics are different. Pretty much everyone is different, and so as such, there's not a one-size-fits-all solution. What that means is that you really have to go out and do a power quality study at the customer site to understand, A, what is causing the harmonic, and then B, what frequency range you were talking about, and then C, how do I tailor a solution basically to fix that. A couple examples of solutions. Most of the time it's going to be a filter of some sort. An active filter basically makes a mirror image of the harmonic. Those of you that have noise canceling headsets uses the same technology. Basically a noise canceling headset, what it does is you've got the music coming in your ears. Let's say you've got some noise outside, maybe your wife's running the vacuum cleaner. What that headset does is it measures that exterior noise, produces a waveform that is equal in amplitude but opposite in phase, sums that together and basically cancels it out. That active filter does the same thing for harmonics on power systems. It measures that harmonic energy, produces a waveform that's equal and opposite, and cancels it out, trying to get you back to a pure sine wave. Same thing can be done with a tune filter. It's effective but expensive in that it's very specific to a given set of frequencies. Once again, the size of the filter may be huge, just depending on how much power you have coming into your system. But that's a very effective way to do it. But once again, it's a very specific solution. You couldn't take that solution and take it down the street to the next guy, because he may have a very different load, very different set of harmonics. And so once again, that's not a one-size-fits-all solution. It's a very specific solution. Third solution was something that another fellow here that I worked with mentioned to me, something called a zigzag transformer. That's something I've actually not had much experience with, actually no experience with in my 30-something years in engineering. But basically, it's used for those third harmonics. You remember the ones that burnt down the clubhouse. So that's an effective way by which you can get rid of that. But bottom line is, if you want to get rid of the harmonics, really it's going to be up to the customer to figure out, what's causing the problem, and then paying some money to get a solution, a customized solution to do that. Last thing I'm going to leave you with today is a couple of power quality standards. I mentioned ANSI. ANSI C12, of course, does that specific to metering. In more general terms, the IEEE, which is the electrical engineering organization, basically has these standards here that deal with all sorts of different things that you have for power quality. So I've got that page and that page. So that being said, that's our presentation for today. Thank you all once again for tuning in, and hope you tune in on Thursday. Thank you very much.